support system. So all you have to do now is to input the data needed, and it will provide the optimal network that would be of benefit to the decision makers involved. So what it solves, it eliminates the numerous choices and provides you the best one based on your objective, and improves the efficiency altogether. So it's composed of the bi-level optimization, fuzzy programming, and cooperative game theory. But the question is, what do these solve in the design process? So in terms of the hierarchy among decision makers, it is solved by the bi-level optimization by being able to model the system accordingly. As for the conflicting objectives between the decision makers, it's comprised of fuzzy programming and cooperative game theory. So fuzzy programming involves fuzzy sets in order to optimize the system. When we're having conflicting objectives, when we prioritize one objective, we can fully satisfy it. However, compromise will happen in the other objective. The same applies when you shift the priority. So what fuzzy programming does, it provides a compromise such that we can satisfy or partially satisfy the objectives of the decision makers involved. So it's a form of compromise between various decision makers. This is a formulation. And in cooperative game theory, it ensures that the effort given of the industrial plants is substantially or properly compensated. For example, if you give 30% effort, you expect 30% of returns to return to you. So this is the formulation. And this is the proposed eco-industrial part that we're going to investigate. So in the method, this is the developed model, it's interaction. So this is the process matrix and other pertinent data. So from the results, once we developed the model and incorporated it into the system, this is the standalone plants themselves. But once we induce the model, we were able to generate this interaction. You don't have to think about it, you just have to input it into the model, and it will provide the optimal network as you desire. So this is the profit of the base case for each of the plants. But once we integrate it into the eco-industrial part, we can see that there is a notable increase in terms of annual net profit. This is the result of a more efficient way of handling the resources. Sometimes we just have to properly allocate it in order to achieve such a significant benefit. The same can be applied when we deal with the environmental footprint, which is the carbon dioxide emission, as well as the fresh water consumption. So once we develop the model, optimize it, incorporate it into the eco-industrial part, we had these benefits. So as a conclusion, through the model, biofuel production from microalgae is commercially available. It's not just an idea. We can actually make it happen once we incorporated microalgae biofuel production to an eco-industrial park. So we can change from a dirty form of energy to a much cleaner one. So in other words, let's make it happen. We have the resources, we have the people, we can do it. And on a short note, we are thankful that our papers have been accepted in various conferences such as in the Leadership Research Congress, to the IEEE 10Con in Singapore last year, and last time in August we went to Tianjin and shared our study, and we are very thankful that we have been accepted to a special issue. And once again, thank you, and let's make a difference, one step at a time.
Thank you very much, Mr. Aguilar. Undergraduate thesis ba itong mga pinipresent itong mga ito? MS or PhD? So our next finalist obtained his BS Chemical Engineering cum laude from the University of the Philippines, Los Baños. So he'll present his research on optimization of bacteriocin production by Pediococcus acidilactici, Linder in rice bran extract based nature. Friends, let's give a round of applause to Mr. Neil Carlo Olegario.
Hello, good morning. Good morning, everyone. I am Neil Carlos Legario, a chemical engineering graduate from the University of the Philippines, Los Baños, and allow me to present to you my research entitled Optimization of Bacteriocin Production by Pediococcus acidilactice in rice bran extract-based medium. Now, let's start with food safety. We may not think much about it, but how can we say that our food is safe to consume? Since some food products do not undergo heating prior to consumption, like milk or cheese, we need to ensure food safety by maintaining quality to the levels of production and storage. And recently, we have also heard news here in the Philippines of food poisoning cases. And a proposed solution to fortify food safety, not just in the Philippines but around the world, is the use of bacteriocins. Now, what are bacteriocins? These are antimicrobial compounds produced by bacteria that can inhibit structurally similar pathogens to the producer. These are usually produced by lactic acid bacteria and are usually part of their natural defense mechanism. And because of these antimicrobial properties, bacteriocins are commonly mistaken with antibiotics. However, they have a lot of differences. Here are some. First, bacteriocins are safe to apply on food due to its proteinaceous nature that can easily be degraded by the proteases in our stomach. Next, it has a high target selectivity and can even be active at minute concentrations. Furthermore, it has a wide active pH range and does not develop any target cell resistance. This is because of its different mode of action. It forms spores on the target cell's cell membrane and inhibits the cell wall synthesis. Next, it does not affect food sensory properties, which is a very desirable characteristic for food applications. And finally, it has no known side effects. There are different methods on the application of bacteriocins. And the first one is through the direct addition of the bacteriocin as a food preservative. Next is through the inoculation of the bacteriocin producer. Third is called hurdle technology, wherein the antimicrobial properties of bacteriocin is synergistically combined with heat or other preservatives. And finally, the last method is called bioactive packaging, wherein the bacteriocins are incorporated in polyethylene films and tin can surfaces. Here are some examples on the application of bacteriocins. The first one is on cheese production, where it prevents the late glowing defect in cheese. And from what we can see in the figures, we can see that in image A, we can have a better quality of cheese by using bacteriocins. Next, it has been proven to extend food shelf life. And also, it has been incorporated in some animal feeds so that we can have healthier livestock. Furthermore, it has been involved in pharmaceuticals, where it was used to treat pathogen-associated diseases and act as an alternative to antibiotics. And finally, it has also been involved in cancer therapy research, where it has been observed to have activity against tumor cells and inhibit bacteria that are connected to cancer initiation. However, despite its promising applications, bacteriocins are not yet commercially available in the Philippines. One example of bacteriocin, named nisin, is the only widely commercially produced bacteriocin in the world, and it is used as a preservative and as spoilage control for the listed products. Another example of bacteriocin, pegicin, the focus of this research, has been observed to have better activity, temperature resistance, and storage time than nisin, and it can be used as a biopreservative and fermentation starter for a number of products. And because of these desirable characteristics, pegicin is said to be the next bacteriocin for commercial production. By the year 2015, the market value for bacteriocins are said to be $442 million US, and it is projected to increase at a value of $546 million US by the year 2020. Here's a summary of its significance. First, it can act as an alternative for potentially harmful substances, and it can supply to the high demand for biopreservatives. It can prevent microbial-initiated diseases, and again, it can extend the shelf life of our food. Here are the objectives that were involved in the study. The first one is to optimize the medium components for pegicin production at the flask level by considering the factors of temperature, carbon to nitrogen ratio, and initial glucose concentration. The second objective was to numerically verify the optimum conditions at the flask level through verification runs, and the last objective was to verify the pegicin production in a 5-liter stirred tank bioreactor. Here's an overview of the methodology. The first step is the selection of the microorganisms. Second is the media preparation, third is medium optimization, and the last step are the bioreactor trials. Let's start with the accession of the microorganism. The chosen bacteriocin producer is Pediococcus acidilactosii, while the chosen indicator organism that will be used to measure the bacteriocin inhibitory activity is Listeria innocua. Listeria innocua is a surrogate microorganism for the pathogenic Listeria monocytogenes, and the purpose for this substitution is for the safety of the researcher. The next step is media preparation, where there were three types of media that were prepared throughout the study. The first medium was for the Pediococcus strain, second is for the Listeria innocua, the indicator organism, and the third one is for the fermentation medium. The fermentation medium was the rice bran extract supplemented with glucose for the carbon source and ammonium sulfate for the nitrogen source. The rice bran extract was prepared by boiling 300 grams of rice bran in 3 liters of distilled water. The medium optimization was performed using the following low and high values for the factors of temperature, initial glucose concentration, and carbon to nitrogen ratio. And a box bank and experimental design with a total of 17 runs was utilized in order to optimize the medium. Also, 3 responses were measured throughout the study, and these were bacteriocin activity, biomass concentration, and residual glucose concentration. And they were all measured using their corresponding assays. After medium optimization, the optimum medium was used in the bioreactor trials, and it was performed with the aid of a 5-liter Biostat A+ bioreactor, and it was operated at the optimum temperature obtained from the previous medium optimization and at an agitation speed of 50 RPM. It is set as such a low agitation speed setting because the Pediococcus strain is a microaerophilic organism. Now let us proceed to the results and discussion. After validating the significance of the statistical models for each response, 3D response surface graphs were generated. And the slide shows the 3D response surface graphs for bacteriocin activity and the effects of initial glucose concentration and carbon to nitrogen ratio on bacteriocin activity are shown at different temperature levels. And warm colors towards red signify high values, while cool color towards blue signify low values. And the desired outcome for bacteriocin activity response is a high value, and this can be observed to be highest at the mid temperature of 37.5 degrees Celsius. And from these graphs, you can see that bacteriocin activity increases with initial glucose concentration until a peak value and decreases thereafter. Also, bacteriocin activity decreases until